Have you ever stopped to think about how your phone can charge from a massive car battery without, completely frying itself? Or how your laptop sips power so efficiently it can run for hours and hours? Well, the answer is this tiny, unsung hero of the electronics world. And in this explainer, we are going to pull back the curtain and see exactly how this little genius works with almost perfect efficiency.
All right, let's just jump right in, because this chart says it all. To really get why this matters, you have to talk about efficiency. See, the old way of doing this, using something called a linear regulator, was just incredibly wasteful. We're talking about losing half the energy you put into it. But look at that comparison. The modern buck converter hits a staggering 95% efficiency. That's not just a little better, that is a massive leap, and it's pretty much the reason our modern gadgets can even exist.
So what's the actual problem we're trying to solve here? It's pretty simple, really. Most of our electronics, they need a very low, very stable voltage. Think 5 volts, maybe 3.3 volts. But the things that power them, like a wall plug or a battery, they're providing a much higher voltage. The old school solution was, well, to just burn off all that extra energy.
And when I say burn, I mean it literally. We're talking about turning that precious battery power into wasted heat. Imagine you have a fire hose, but you only want a gentle trickle of water. The old way was to just put a giant board in front of the fire hose to block most of the water. It's crude, it's messy, and it wastes a ton of energy. That's a linear regulator for you, a device that could throw away up to 60% of your power.
Okay, but there is a much smarter way to do this. The buck converter doesn't burn anything at all. Instead, what it does is it cleverly chops up that high-voltage electricity into these tiny little packets, and then it averages them all out to create the exact lower voltage you need. So it's less like a brake and more like a super fast water faucet, turning on and off millions of times a second to give you the perfect flow.
So how in the world does it pull off this magic trick? Well, it's all thanks to a tight-knit team of 4 key components, all working together in perfect harmony. You can think of them like a little coordinated crew, where each member has a very specific and very crucial job to do. So let's meet the team.
First up, we've got the switch. This is usually a component called a MOSFET, and you can think of it as the brain of the whole operation. It's an incredibly fast gate that's opening and closing, sometimes millions of times every second. And it does this using a technique called pulse width modulation, or PWM, which is really just a fancy way of saying it has precise control over how long it stays open during each little pulse of power.
Next on the team is the inductor. And honestly, this is where the real magic happens. Think of it like a temporary battery for energy. When the switch is on, the inductor stores up energy in a magnetic field. But its most important feature is something like inertia. It absolutely hates any change in the flow of current, so it works to keep that electricity flowing smoothly even when the main power source gets cut off.
Our third player is the rectifier, which is usually a simple diode. Its job is to be a one-way street for electricity. So when that main switch turns off, this one-way gate automatically opens up, giving the energy that's stored in the inductor a path to keep flowing out to the device. It's what keeps the lights on, so to speak, even when the main switch is off.
And finally, the last member of our crew, the capacitor. Now, all of that high-speed on and off switching creates a pretty choppy, pulsating current. The capacitor's job is to act like a small reservoir or a filter, smoothing out all those jagged ripples and delivering a clean, stable DC voltage that our sensitive electronics can actually use without freaking out.
Okay, so we've met the team. We've got the switch, the inductor, the rectifier, and the capacitor. Now, let's see how they all work together in this incredibly fast, two-step dance of storing and releasing energy. This is the absolute core of how the buck converter does its thing.
The entire process really just boils down to these 2 phases, happening over and over again at lightning speed. First, the main switch turns on, and the circuit stores up energy. Then, the switch turns off, and the circuit releases that stored energy. Store, release. On, off. That's it. It's that simple.
All right, let's break down phase 1. Switch on. Current starts flowing in from your battery or wall adapter. It goes right through the inductor, which immediately starts building up its magnetic field. It's basically charging up with energy. At the exact same time, the capacitor is delivering smooth power to your device. And that one-way rectifier gate, it's closed, blocking the path. Now for phase 2. The main switch flicks off, instantly cutting the circuit off from the power source. But remember that inductor and its inertia? It doesn't want the current to stop, so its magnetic field collapses, releasing all that stored energy and turning the inductor itself into a temporary power source.
This release of energy forces that one-way rectifier gate to open, completing the circuit so that power continues to flow to the output, totally uninterrupted.
So you might be wondering, how does the converter actually control the final voltage? How does it know to output 5 volts and not 3 or 9? Well, it all comes down to one simple concept, the duty cycle. And that's just the percentage of time that the main switch is in the on position during one of those full on-off cycles. This is the master control knob for the entire system.
And what's so beautiful about this is how elegant and simple the math is. The output voltage is just the input voltage multiplied by that duty cycle. So if you want the output voltage to be half of the input, you just set the switch to be on for 50% of the time. It is a wonderfully direct relationship.
Let's make this real. Let's go back to our car example. To get that stable 5 volts that your phone needs to charge from a 12-volt car battery, the buck converter switch just has to be on for 42% of each tiny cycle. That's it. By precisely controlling this timing, it can produce any lower voltage it needs with incredible accuracy.
Okay, so let's circle all the way back to the beginning. How does this all add up to that incredible 95% efficiency we saw in that first chart? Why is this method of storing and releasing energy so much better than the old way of just, burning it off as heat?
Well, it really boils down to 3 key things. First, and this is the big one, energy is being stored and then transferred, not burned away as waste heat. Second, the components themselves have gotten incredibly efficient. Those MOSFET switches have almost zero resistance when they're on. And finally, for the most advanced designs, they even replace that simple diode with another super efficient switch, a process called synchronous rectification, which cuts down those tiny energy losses even further.
And there you have it. The buck converter really is a perfect example of elegant engineering. It's this tiny, totally invisible circuit that is saving a phenomenal amount of energy every single day, inside billions of devices all over the world. And it kind of makes you wonder, doesn't it? What other invisible efficiencies like this are quietly and perfectly powering our modern life?